Hello, I'm your host Pankaj Basnal, and you're watching Coding Quest, a YouTube series where I experiment with different programming ideas and prototypes, and this time we are writing a simple but working implementation of ECS. Before I begin, I want to clarify that the implementation shared in this video is my own, which I wrote after reading through multiple internet sources and performing multiple experiments. I'm as new to this coding style as any viewer of this video might be. So feel free to point out my mistakes or leave any suggestions on how I can improve this implementation. You can also check the code on GitHub and comment there if you wish. With that covered, let's quickly gloss over the main concepts of ECS, which will be explained as we move forward. On the surface, it's like an assembly line, with each system performing its specific operation by working on the component assigned to it, and once it's done, the entity is passed on to the next system. So, on the surface, apart from said entities, systems, and components, we need an operator of the assembly line itself. This operator should know what type of entity we are building and what systems are required to build it. This operator will be called entity archetype in the rest of the video. More on the archetype later. And below this surface, we have the whole mechanism of the assembly line itself. The assembly line holds all the entities and components. It is responsible for moving them from one system to another. Suffice to say that this line makes the assembly possible. In my implementation, this is built using an object pool, which in turn uses an expandable array data structure. Both of these are a bit complicated and will be covered later in the video. But first, let's explore the surface for a bit. Components contain the data required by one or more systems of our application. By decoupling functionality into distinct and small components, we can easily add or remove features without disrupting the entire code base. This has been covered in the last video, so do check it out if you haven't already. Systems, on the other hand, are the workhorses of ECS. They consist of a set of steps that are executed on specific components. Systems operate independently, making them highly reusable and allow for efficient parallel processing. This design promotes better performance, scalability, and flexibility of our application. An archetype is the operator who defines the type of entity it can work with and manages its execution cycle. Think of it as a man holding a blueprint for creating and managing entities within the application. In the world of ECS, an entity is the most simplest object. It only needs to contain a number which is used as an identifier, like a phone number. But the entity itself doesn't contain any information. So we define an entity by specifying which components are part of it. This in turn controls which system will work on the entity as well. To really understand how an application will work, imagine that the application requires two systems, sort setter and sort system. The sort setter generates an array of random numbers, and the sort system will reorder those numbers using the bubble sort algorithm. To build this application, Archetype will create an entity by adding two predefined components, initialization and finalization components. This signifies the birth of the entity and its entry into the world of ECS. The newly created entity is kept on the shelf for the time being. The shelf is a virtual concept. It's not actual code. It represents a state during which none of the systems can operate on the entity, since we have not defined it yet. This allows the archetype to control the exact time when the entity can be defined during the execution cycle. At the start of every execution cycle, the initialization system takes the stage. It iterates over all entities that are on the shelf and finally defines them by adding the required components. This signifies that the entity is now ready for further system processing and is no longer waiting on the shelf. The component that we will add is the sort number component, which is required by sort setter and sort system. Now that our entity is ready for action, the sort setter adds an array of random numbers to the component, and by doing so, it provides the data required for the sort system to work its magic. The sort system springs into action, sorting those numbers by using the bubble sort algorithm. It operates on the sort number component attached to our entity transforming the data into the desired order. At the end of the execution cycle, the finalization system takes its turn. It cleans up the assigned components and the entity for future reference and recycling. And there you have it. The execution process is complete, with each system playing its part in shaping the behavior and state of our entity. To quickly recap, in ECS, we create entities by adding initialization and finalization components to them. These entities then reside on the shelf, a virtual concept where they wait for further processing. The initialization system steps in first during the execution phase to add the required components, and once that's done, the entity is processed by our application and is finally cleaned up by the finalization system. In my implementation, Archetype creates multiple batches of entities, and each batch is processed in parallel to one another by the systems. Have you noticed how sort setter and sort system don't actually need to know about the entity itself? All they really care about is the sort number component. This is also true for almost every other system that we may need. This fact is exploited by ECS to optimize memory access. We first store the components in an array independent of the entity. Once that's done, every system can just iterate over the component array and perform its operation without ever knowing which entity it's operating on. We can now optimize our arrays by rearranging elements within it so that all the components that are being used can be kept together and the components that have been used are kept together. We can also reuse the components of new entities, which helps to maximize the benefits of CPU caching while minimizing the GC overhead. The data structure that can support this type of memory management is called an object pool, and it's a key component of our ECS architecture. The object pool serves as a reservoir of reusable objects that can be shared across the systems, and since we are reusing objects instead of creating new ones every time we need them, object pool helps in reducing the overhead of garbage collection. By utilizing an array-based object pool, we ensure that the objects actively in use by the code base reside consecutively in memory. This arrangement prevents fragmentation and allows for efficient use of CPU cache while a system is operating on its objects. In other words, it maximizes CPU cache utilization, resulting in improved performance. The object pool presents us with several essential operations to manage object allocation and deallocation effectively. To get a new object when our application needs it, the object pool will return the index of the last in-use object plus 1 and then increment the last in-use object index. To free up an object after the application has used it, the application will return the used up index to the object pool. And to free it, object pool will take the object at the last in-use index, move it to the used up index, and then decrement the value of last in-use index by 1. This way we maintain a continuous block of in-use objects. But this will create a problem since the last object is not at the index which was shared with the application anymore. To address this problem, object pool has an auxiliary array of integers. This array maps the indices that were shared with the application to the actual indices of the objects in the pool. This ensures that the application can access the desired objects reliably, even as objects are rearranged within the pool. For memory optimizations, we have used arrays, but arrays have a big limitation. Their size is fixed. But for the object pool to support a scalable application, it should have the capability to expand on demand. So it doesn't use the arrays as is. It uses a data structure called expandable array. Expandable array, as the name suggests, have the special ability to grow dynamically as needed. In fact, it doubles in size when necessary. This means that as more entities and components come into play, the expandable array expands to accommodate them. We could have used a list, which essentially provides the same functionality. But this whole architecture is about high performance, and expandable arrays provide significant performance advantage over standard lists. The expansion is a simple process of creating a new array which is double in size and copying all existing data to the new array. So keep in mind, that it does have some maintenance cost, although negligible in most cases. While this implementation works, it does have some concerns and limitations. This architecture has a lot of overhead of maintaining the entire functioning application. This overhead includes memory swaps, array expansions, and an auxiliary array to correctly find the object in memory. Another limitation lies in the component arrays, which are being allocated on the heap memory, despite being structs themselves. While this may impact memory allocation, it still allows for CPU cache optimization due to the contiguous nature of the components array. Also, the optimizations won't work if the components contain reference type data members, since those members will be allocated at some random location in the heap memory. Systems are also limited in the number of components that they can take as an input. Right now, it's just one. This might restrict certain use cases, so it's important to design systems that work on simple and small data types to maximize performance and maintain a clean architecture. Lastly, object pools and expandable arrays are not inherently thread safe. For now, concurrency issues can be avoided by allocating or freeing components only in the initialization and finalization phase. And that's a wrap on my basic implementation of entity component system in the .NET environment. While it may not reach the mind-boggling levels of performance achieved by industry giants like Unity, this journey has been incredibly educational, providing valuable insights into the world of .NET, ECS, and software in general. It serves as the groundwork for future quests that I'll be starting after this. I'll continue to work on this framework as and when I use it in my other projects and get a better sense of its performance in real applications, but that will have to wait for future quests. So thank you for joining me on this quest, and I'll see you soon on the next.